So now we know that the oscillations are in the brain, we know how they are made, and we know why they are important. Now we need to find out how could we analyze these. So the theory is now behind us. So let's go to how do we analyze this oscillatory data. And the most important thing that you have to think about here is that we use something called a Fourier transform. And why is it called a Fourier transform? That's simply because Fourier came up with the way to dissect a signal into different oscillatory patterns. And to really explain the Fourier transform, and especially the faster Fourier transform in this particular lecture, goes a little bit beyond the scope of this lecture. So we're going to keep it a little bit easier, but still I want to do like a step-by-step basis of usually how a Fourier transform is calculated. Let's say we have our signal here, and we want to find out how much oscillatory data is in there of 2 Hz. So for the frequency of 2 Hz. How can we do that? So we have our graph down here, and we want to find out, okay, 2 Hz, how much power in frequency is in there? So how much of that frequency is in this data? Well, what we can do is simply come up with a sine wave, a 2 Hz sine wave, which is equal in length to our real data. Let's say our real data is 10 seconds. We have a very short recording, and we have a sine wave of 10 seconds. So it goes up twice and down twice every second. And now we're going to compare these two signals. Simply, how similar are the two signals? How well do they fit each other? It's a simple fit, actually. And they do this with a dot product, and what exactly a dot product is goes a bit beyond the scope of this lecture. But maybe if you want to know more about the Fourier transform, you can always look it up online. And then we find out, okay, the similarity, and we basically put that in the graph down here. So this is the similarity of 2 Hz between the 2 Hz wave and our original signal. And we can also do this for 4 Hz, and we can also do this for 6 Hz. But as you see, there's actually quite large gaps in between the numbers, so now we have to fill in a line. So maybe it's better to go in smaller steps and then all the way from 1 to 20 Hz. So let's do that all after each other. So this is basically a frequency spectrum. So now we have analyzed this whole signal based on what types of frequencies are in the data and how much of these frequencies are in the data. And what you notice straight away is that this has this very well-known sort of model that goes from an asymptote to the y-axis to an asymptote at the x-axis, which is basically a logarithmic scale. So it's 1 over x. And you see that any sort of neural activity usually has this frequency model. It looks this way, right? But also, if you notice, if you pay close attention to the details here, you see that there's a small peak here around the alpha frequency. This is data of an infant, and between 6 and 8 Hz, that's alpha frequency for infants. And this conveys some sort of information. And basically what it means is that this information was gathered from an infant at rest, and in an at rest brain usually you have a little bit more alpha activity than in an awake brain. Or we could also let them close their eyes for a minute, and then you would see a very big peak here, because then there's a lot of alpha information in the brain, especially in the visual parts of the brain. So with this, now what we basically have done is look at the whole data set, everything together, and basically we've determined how much of each frequency is in the data set. And with this, you can do a couple of studies, and one of the nicer studies has been done quite a while ago now. It's almost 15 years ago. It's been done by Jensen and Teshi in 2002, and they basically looked into working memory, and they wanted to find out which type of frequency was involved in working memory. And what they did is they did a very simple working memory paradigm in which subjects were asked to memorize what was on the screen. So basically at the baseline where nothing was on the screen whatsoever, they had a crosses category in which there were only crosses on the screen. And usually this is not that difficult because you can count the crosses and then store simply one number. So it's basically, okay, there's 7 crosses, so it's 7. So it's one number in your working memory, so it's not that difficult. Or they had a different category in which there were digits on the screen, which you had to remember which kind of digits were on the screen, and this is a lot more difficult. So it's a lot more taxing on your working memory, and what they found is, and this is the same frequency spectrum as we had before, only we had a bar plot, they have this line plot, And basically you see it going up here. So this is from 4 to 14 hertz. So probably if this goes to 0, you see this will go all the way up there and this all the way down here. And you see a very specific peak around 6 to 8 hertz. And 6 to 8 hertz in adults is actually theta. And they found out that the more load you have in your working memory, the bigger this theta peak. And they also found out that specifically in the digit category, if you had a very low memory load with digits, for example, if you only have one digit remembered, then you can see here this dotted line is the lowest one here. And if you have a very high memory load, you see actually a very high peak. So it seems as though the more you use your working memory, the more theta is actually present. And this is theta that's present in the frontal areas of the brain, so the left and the right side of the brain. So this basically shows you that you can very easily get frequency information from your data, and that this frequency information can oftentimes be linked to particular behavior. But I think it's time for a question, and maybe you guys already had a kind of a feeling that this was coming, but can you maybe think of any disadvantages of using this Fourier transform to determine frequency data for the full data set? And I want you to think specifically about what kind of information you lose. So the main disadvantage here is that you lose dynamic information. And the dynamic of the information that you lose is especially frequency information over time. Because let's look back at our frequency spectrum here. We see that for every frequency we have simply one value. So this means that we average together the complete frequencies of the complete task and average them just in one value. So you lose a lot of frequency information. And just to give you a basic example of why this is worrying, let's say you have a task in which alpha is very important. But you see these big bursts of alpha, and afterwards you see these big sort of depressions of alpha. So there's less alpha than normal, which is also information, right? If there's something more than is necessary, than we would expect, it's information. But if there's something less than we would expect, it's also information. And if you average this together over a whole trial, then all of a sudden there doesn't seem to be any sort of alpha activity during the experiment, while there was a lot of information in alpha. So we lose this information. So